All right, so we're going to go ahead and talk about the beam design. The first beam design we're going to do is going to be on paper in the packet. It's going to be the interior beam. The other ones we're going to do exterior beams. We're going to do a girder, an interior girder, and an exterior girder. Okay, so for the interior beam, if we're looking at this page, it's a beam along column line. Well, they didn't say column. So it's going to be interior beam along either like any one of these beams, like this one here, this one here. Any of these are interior beams. Okay. The reason it makes a difference compared to an exterior beam is, right, if this is an exterior beam, it's all about contribution area. Remember, we talked about this with the joists for an interior beam. I'll go to a clean one over here. Right, you split the load. This area goes to this beam. This area goes to this beam. Okay, and then same thing here. So our contribution area is that width there, and then that width there. And it's 10 feet in between each beam. So this is 5 feet, this is 5 feet. Therefore, the total width of the contribution area is 10 feet. Really important thing to know. Width of contribution area. All right, also the length of these beams is important. 24 feet is the length of the beam. Okay. And this is the actual beam itself here. All right. All right, so loading for our beam. So we have to, since it's indoors, you don't need to consider, because ours is on the second floor, holding up the roof there. We don't need to consider environmental loads, right? I know we're really only designing for the interior portion. If we were going to do the exterior portion, meaning the part underneath the what's it called, the green roof, that would be another set of calculations. Anyways, we're just going to do this once. So, dead load. Normally, you would actually try to estimate what the true weight of the materials are, right? You have the floor above it. You have the steel itself, the steel beam itself. All right. You would go through and try to estimate what all those things weigh. We are going to just make a simplifying assumption to get ourselves started. We're going to just say 50 pounds per square foot for dead load. That's the weight of the materials. All right. Live load. It comes from the International Building Code. All right. So in IBC, right here, for a library with stacks, that's the worst loading situation for us, 150 PSF. Okay. Some other important stuff. The yield strength of steel, structural steel. I've linked a reference material here to show you it. But basically, it just, it kind of shows this graph here, this elastic limit, strain hardening. That's what I was looking for. I knew it wasn't yield hardening or yield strength. It's strain hardening. So if it strains, if it actually elongates, it actually gets a little bit harder up until the point where it reaches its maximum, then necking and failure. And that's where things get really bad. All right. So this thing tells us the modulus of elasticity, is 29 million psi, and then the yield strength. Where did I see the yield strength? It's in here somewhere. Okay, they're saying 36 KSI. I've used 50 KSI a lot. Yeah, I've used 50 KSI, for example. Okay, yeah, so we'll use 50 KSI. KSI is 1,000, so that's why we're going to use 50,000 PSI. KSI is just a simple way to write 1,000 PSI, something you get used to. All right, so those are some important numbers we will use. So, determine the total load. Total load equals dead load plus live load is 50 PSI plus 150 PSI. Hopefully we don't need a calculator for that to know that that is 200 PSI. Determine the contribution area. All right. So the beam, as we said, is right down the middle. And then we have it's 10 feet wide by 24 feet long. 10 feet wide by 24 feet long. We don't actually need the square footage, but if you need that, it is 240 square feet. The really important things, we need the length and the width. Okay? It will help us to have these things in inches. So this is 120 inches wide, and then 24 times 12 is 288 inches. Those are numbers we'll use at various places. Sometimes it's better to have it in feet. Sometimes it's better to have it in inches. All right, uniformly distributed load, pounds per linear foot. All right, so remember, that's where every square foot here, needs a different color. We have 200 pounds pushing down on that one, 200 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 on it. And there will be 10 of these all lined up, right? Because it's 10 feet long. So W is the total load times the width, which is 200 PSI. Or sorry, this is PSF. I apologize. Pounds per square foot times 10 feet. That gives you 2,000 pounds per linear foot. Again, I'm kind of going fast because we did this same process for the roof calculation. All right. Again, it will help to have this in pounds per linear inch as well. A quick dimensional analysis. If it is 2,000 pounds pounds per linear foot per 1 foot, to figure out this in pounds per linear inch, your unit conversion, if we multiply by 1 foot per 12 inches, it explains why we are dividing by 12. So 2,000 divided by 12, you get 166.67 pounds per linear inch. And I'm obviously rounding that last value there. Draw a beam diagram. Well, we've done plenty of these, or we've at least seen plenty of them. You have a pin side there, a roller side here. And this is a uniformly distributed load of 2,000 pounds per linear foot. And this thing is 24 feet long. You have R sub A and R sub B. If you recall from our work through the beam analysis, when we're in this situation here, pretty much all of our situations, the maximum shear is the same thing as the reactions at A and B. And then to figure out what this is, all you have to do is go to the back of the packet where we have our beam formulas, and it's this one here. The reactions are WL/2. W is 2,000 pounds per linear foot. Since we're already in feet, we'll stay in feet, so times 24 feet divided by 2. So 2,000 times 24 divided by 2 gives us 24,000 pounds. So that's the maximum shear. Any questions before I flip the page? Okay. All right, on to the moment. Again, we have a formula for that. All right, like it's right here. WL squared over 8. So 2,000 PLF times 24 feet, that quantity squared, divided by 8. See, 2,000 times 24 squared divided by 8 is 144,000 foot-pounds. All right, the actual design moment is you apply a factor of safety of 1.67. So M sub n is 144,000 foot-pounds. That's the maximum moment we expect our beam to ever be to experience. But what we design for is one that can withstand a moment of 240,480 foot-pounds. All right, this is what the maximum we ever expect, and this is the one that our beam is being designed for. All right. Just because of the way things are, you don't actually use the moment when you go to the beam table. You use this thing called the plastic section modulus. What you do is you just take this value of 240,480 foot-pounds, and you divide by basically they refer to it as the strength of steel, the yield strength. So we're using 50 KSI steel or 50,000 PSI steel. All right. You possibly notice an issue right now. We have foot-pounds, and we are divided by something in pounds per square inch. That doesn't work too well. You can't, just divide feet and inches. They're not the same units. So we actually should go back up here. And so we have 240,480 foot-pounds. They're both in the same thing. I'm just going to put that over top of 1 to make it a fraction. And again, I want to get rid of my feet and change it to inches. So I multiply by. I want to get rid of the feet. The feet's in the numerator, so I do 1 foot per 12 inches. Feet go away, so this hopefully explains why we actually, in this case, we multiply by 12. 240,480 times 12. And so we get, I think it's 2 million, or no, 28 million. Do that again. 2885760 2,885,760 inch pounds. Okay. So it's 2885760 inch pounds divided by 50,000 psi. And if you want to do the unit analysis, it's inch pounds divided by pounds per inch squared, which is inch pounds times inches squared per pounds, pounds divide out, inches times inches squared is inches cubed. So we get whatever this number is going to be in units of inches cubed. So divide this by 50, 1, 2, 3, and we get 57.7 inches cubed. Don't worry about the units, worry about the number. 57.7 is what we need to figure out. And so if you want to, this is a QR code that you can scan with your phone, and it will bring up this website. I'm going to use it right here. This is a beam table. All right, so, or it takes you to the website with the beam tables, and we need properties. So it's plastic modulus Z sub x. You see it's in inches cubed. We just need one that is higher than 57.7. So we scroll down. A lot of these are way stronger than we need. Oh, we're starting to see ones here. Oh, right here, W12 by 40, not quite strong enough, but W12 by 45 is good. I could go a little bit smaller if I wanted to. The W12 by something, the 12 indicates the thickness of the beam, the height of the beam, and the second number by 50, by 45, that's the weight of the beam per linear foot. All right, so that's what those numbers mean. I'm going to intentionally pick the wrong one to kind of just show you what could happen here. Say I'm just not paying attention, and I choose the W12 by 35, all right, which has Z sub x being equal to 51.2. Some other important information we're going to need here. We're going to need D, the depth of that one. D is, we need dimensions here. 12 by 35. The depth in inches is 12.5 inches. We're going to need T sub W, the thickness of the web. T sub W is 0.3 inches. And do we need anything else? We need D, T sub W. We need E and I. E is a standard thing, but I is a property for a W12 by 35 here. I is, it's right here. It's I in the, I can't remember. Is it X or Y axis? I believe it's the Y axis. I is 24. Let me just write down both of them in case. I sub X. I in the X direction is 285, and I in the Y direction is 24.5. And those are both in units of inches to the fourth. Okay. I just can't remember off the top of my head which one I need right away. All right, so there's that information right there. And again, remember, I intentionally chose the wrong one just to show you what could happen if you're just not paying attention, but also to show you how nice our spreadsheet's going to be when we get that up and running. All right. Check the shear capacity. So another concept around a factor of safety. So rather than increasing the load like we did with the last factor of safety for the moment, remember we did that over here, 1.67, increase the load. What you also can do is you can use a factor of safety to decrease the strength. All right, so instead of the concept of saying, oh, the beam needs to carry a load of 100 pounds, so I'm going to make it that it can carry 150. Well, I could also say, well, my beam can carry 100 pounds. Well, instead of it saying I want it to carry like the maximum capacity, I only want it to carry 60% of its maximum thing. So there's different ways to do that. So that's why we decrease the strength of what we assume, but at the same time we increase the load by 1.5. So it's really just making things stronger than we think they need to be. Okay, so V sub n is 0.6 times 50,000 psi times the depth of the beam, which for our W12 by 35 is 12.5 inches, and the thickness of the web was 0.3 inches. So basically what they're saying is this is 0.3 inches that way, 12.5 inches that way. It's only the web. They are not talking about the top of the eye or the bottom of the eye, and the shear is all being carried by that, nothing by that. Again, another conservative estimate. All right, so all the shear is being carried by the web in the middle. And if you do this, we are assuming that our beam can carry, so 0.6 times 50, 1, 2, 3, times 12.5 times 0.3 is 112,500 pounds. That's the shear strength of our beam. V sub A, this is the applied shear. We did that all the way back in step F, 24,000 pounds. So 24,000 pounds times 1.5. So again, we're even increasing that. 24, 1, 2, 3 times 1.5. You get 36,000 pounds of shear. That's your applied shear. What you care about is this number bigger than this number? Yes. All right, the shear strength is bigger than the applied shear. We are good. All right, now let's check deflection. All right, what's the maximum allowable deflection? And it's best to talk about this in units of inches. So let's take the length of the beam and divide it by 240. So 24 times 12 is 288 inches. So max allowable deflection is 288 inches divided by 240. All right, that's just, again, a rough estimate that engineers have found over time that people feel safe, and for whatever reason, it's an easy calculation and people feel safe if they have that little deflection. So we are allowed to have 1.2 inches of deflection. So crazy enough to think, once you put that beam on, it will flex down in the middle about 1.2 inches. Well, let's see if our actual beam meets that. So the calculation for what is actually expected is 5 times W. W was our 2,000 pounds per linear foot, times L to the 4th power times 24 feet to the 4th power over 385 times E, which was 29 million psi times I. Let me check something here. I have it in this sheet. I is the x direction. Okay, so we wanted the x direction. Glad I wrote down both. The x direction was 285 inches to the fourth power. All right. Well, again, you might be noticing we have feet in the numerator and we have inches in the denominator, and we wanted it in inches. So if we just do some quick updates to our numbers in the numerator, it will help us. So remember, back here in part D, we already did this actually. We already did the uniformly distributed load in pounds per linear inch. So all we got to do is replace the 2,000 with that number, 166.67. And then 24 feet also in inches. We already did that. It's 288 inches to the fourth power. Okay? So always got to keep your units in order as an engineer. And let's just do this math. So it's a fraction, 5 times 166.67 times 288 raised to the fourth power, divided by 385 times 29 million times 285. Want the answer as a decimal, so I'll just do that. 1.8 inches. Again, this is our max allowed. This is expected. We have a failure. Not that the beam itself would fail, but it's too much deflection. People are going to get nervous. This is not the correct beam to use. Pick a different beam. So at this point, if we were still doing this by hand, we'd have to go back to part J, pick a new beam, get the information, go back to K, recalculate, back to L, recalculate, back to M, back to N. All right? That's the nature of engineering is, when you first start out, you might not know some stuff. As you get better, you just know, oh, I usually use this beam or this beam or this beam, and you just get more practice with it. All right? Or what you could do is say, hey, this is a lot of repeated calculations. You know what's really good at a repeated calculation process? A computer. So let's have a computer do all this stuff for us. All right, so at this point, my recommendation is for you to go to the Google Classroom and open up this sheet. Every single one of you have your own sheet available to you. All right. If you try to type in the numbers here and here and here, things will not go well for you. What you really want to do is follow me and type in the formulas, because then things will actually work for you. All right. I've had that before where students just copy the numbers that resulted, and then in the end, everything didn't work. All right? Because I'm going to, again, my first time around, I'm going to intentionally choose the wrong beam, and then when we go back and pick the right one, you'll see that all my numbers automatically change and all your numbers don't. So please, 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 other than the yellow cells, type in formulas. Only in the yellow cells do you type in numbers. Does anyone have any questions about that? All right, so in the yellow cells, the dead load is 50 PSF. Remember, that was an assumption. The live load was 150 PSF. Oh, the other thing is if you have two screens available, work off of one screen and look at another. Otherwise, I would split your screen, hopefully so that you can see what's going on my screen. And then what's going to happen on your screen, or just watch the recording later and catch up, because this isn't super complicated stuff, but if you type the wrong thing in, it will. All right. Other things we need. The yield stress of steel was 50,000, so 50,000. So number 5 and then 4 zeros. Young's modulus, 29 million. So 29 and then 6 zeros. 1, 2, 3, 4, 5, 6. Enter. The length of our beam was 24 feet, and the width of our contribution area was 10 feet. I am done typing in actual numbers. The rest of what I'm doing is going to be a formula. So when there is a formula, always the first thing you ever type is an equal sign. So in total load, I'm going to say equals. And then I'm going to click on the dead load number. So click on this cell. Just click one time and see how B4 shows up. And then I'm going to click, hit the plus sign, plus, and then click on the live load number. That plus that. So again, when things change, if I change the dead load to, say, 75 PSF, it automatically updates. I'm going to go back to 50. If the live load changes to 100 PSF, it changes. All right? Change everything back. All right. Pretty easy formula. Equals, and then just add two values. All right, the length. Again, a super easy formula. You're converting from feet to inches. So equals, click on the 24 one time, times, meaning star, either the star key on your number pad or shift and 8, and then times 12, right? Because you're converting from feet to inches. Again, with the width, convert from feet to inches, equals 10 times, click on 10 times 12. Do not type in the number 10, click on the number 10. All right, whenever you click on something, the cell number and letter and number automatically shows up. All right, area equals length times width, and I want it in square feet. Notice how I always tell you the units right next to it. So equals, click on the 24 feet times, again, times a star, so shift 8, and then click on the 10. Hit enter. And again, if you're missing anything, if you missed something, either just don't worry about it because there will be a recording, or stop me and ask a question because the recording is still going on this time. All right. Well, again, any questions? Also, don't forget, you can also check your numbers because they're all the same so far. The total load, 200, and we see that. In part B, 240, we just got that. Now we're on to part C. This is all lining up with our calculations in our notebook. So part C, the uniformly distributed load, okay? The total load, all I am doing is essentially copying this value down. I'm going to say equals, and I'm going to click on the 200 up here, and then I'm just going to hit enter. Again, you're going to see that happen a lot. If I use a value, I'm going to essentially copy it into the area where I am using it. The width in feet equals, I click on the 10, and I just hit enter. Again, I'm just copying the relevant values for this section of the calculation. And then remember the calculation we actually did in part C was the total load times the width equals 200 times 10. And I'm just clicking on them, and then it shows me 2000 PLF. And again, I can go to my answer that I did by hand and verify I'm getting the right number. In part D, I wanted to use this uniformly distributed load W. Again, just copy that value. And then now I want the same value, but I want it in PLI, pounds per linear inch. So I say equals, and I click on the 2000, and I divide by 12. Again, let me just show you why all of this is relevant. All of this is good. If, again, I change my dead load, all of a sudden I realize, oh, my dead load's wrong, and I need it updated to 60 PSF. If I type in 60 up here, notice how everything just changed in these cells. Okay, if I go back to 50, it all changes back again. Also, down here, if you're frustrated that, oh, it's not 167, it should be 166.67. Well, again, Excel actually, or Google Sheets actually has that value. You just need to have it shown up here. You see these zeros, the 0.0 with the arrow. This one is decreased decimal. No, we want to see more decimals. We want to see 2 of them. You can just click it twice, and now I see the decimals. Again, Excel, or the actual value is there under the hood. You just you just need to see more of it. All right, beam diagram already drawn for you. I just took a screenshot. Part F. Now we're calculating the maximum shear force applied to this beam. I even took a screenshot of what the formula is, WL divided by 2. So let's copy W. We want the PLF version. So equals, go to where it's PLF right here on the 2000, hit enter. We need the length of our beam in feet. So hit equal, go find the 24, click on it, hit enter. And then W times L divided by 2. So equals, click on the W, 2000, times the 24, click on that. And then divide by, which is a backslash, and then it's divide by 2. Hit enter. And again, all these values can update automatically. If the beam is actually going to be 25 feet long, see how everything updates for you. All right, again, one of the big purposes of using a computer. Maximum moment, okay? Again, we need to copy the W in feet, in PLF, so equals, go find W in PLF, click on it, hit enter. Copy over the length also in feet, equals, and then 24. All right, we need the maximum moment, WL squared divided by 8, equals W times L. If you want to do squared, you can do 2 things. You can use the caret, which is shift and 6, to the power of 2, or it's only, times itself, times 24 again. I don't know, I like this one just because then I can do divided by 8 and not have to worry about it. If you choose to use the caret to the power of 2, you have to use a parenthesis. You have to have this in parentheses, otherwise it's going to divide the 2 by 8 and have issues. All right, so if I just did equals this times this squared divided by 8. Oh, did that actually work? I was assuming it would divide the 2 by 8, but apparently it's smart enough not to. Okay, I didn't, maybe that's an update from what I've seen before. Either way, your call, whichever one you want to do. All right, so the max moment, but I also need it in inch pounds. I even tell you in inch pounds, just take the foot pounds, multiply by 12. So equals, click on this number, times 12. Let's verify our numbers, check our numbers from when we did the hand calculations. In part G, in part G, we did the foot pounds. We just didn't convert it to inch pounds right away. So we're not going to verify this number, but we can verify that number. If we needed to, we can verify this number easily. All right, so everything's been going well so far. Now, the nominal moment, meaning apply our factor of safety of 1.67. So equals, click on the max moment, times 1.67. All right. A cool thing about Excel is if you just grab this bottom node, so you move your mouse over to the bottom right corner and you just click and then drag down, it copies the formula for you. And because I just took this value multiplied by 12, I can also take this value, times 1.67. I can take that value times 1.67, and it did that for me. Again, if I check my values for part H, 240, 480. Oops, I clicked something weird. Try that again. 240, 480, 288, 760. Awesome. Everything's checking out still. All right. Hello? All right, so now we need the plastic modulus, which is the maximum moment in inch pounds. Make sure you choose the right one. So equals, make sure it's the 2885760 one this time. In inch pounds, click enter. Copy the yield stress of steel equals, click on the 50,000 up here. And then the calculation is just m sub n, the nominal moment divided by the yield stress. So equals, click on the 2885760, backslash for divide, and 50,000. Click on that number and enter. Hey, 57.72. I remember that number. Yep, it shows up right here. All right, now this is where we have to get our beam information. At the bottom of your screen, you should see 5 different tabs. One for interior beams, one for exterior beams, interior girder, exterior girder. And then this one at the very end, wide flange beam table. If you remember, this website here has all these dimensions and properties for different beams. Well, what I did was I just copied and pasted all that information over to this tab right here. All right, it has all the information we'll ever need. It has the beam names. It has all the dimensions, and then it also has the properties. Okay, which is good for us. Okay. So what we're going to do, go back over here to interior beams. Also, I created a pull-down table, a pull-down list. Okay? So I'm going to move all this. I can hide this stuff. I don't need it. Hit escape. I'm going to grab the W12 by 35, so scroll all the way down till you see W12 by 35 and then click on it. Okay. Now what I want is I want the Excel sheet, I want this sheet to look up these values for me. Otherwise, what I have to do is otherwise you'd have to go here, scroll all the way down. It's going to be really annoying. Scroll all the way down to W12 by 35, and okay, here's my W12 by 35. Oh, whoops, what values do I need? Well, there's a way to do this, and it's not that much work, but hey, if the Excel sheet can do it for me, if it can look up the values for me, why would I do this? All right, and hey, it's really cool. Excel does have a lookup function, and so you have to be careful here. Please follow my my lead here. The only thing I need to remind myself is, let's see, Z sub x. That's in the 19th column here. Okay, so I need to remember the number 19 because Z sub x is in the 19th column. All right, so if I type in equals, the function is called VLOOKUP. The letter V and then LOOK up, open parentheses, turn on, okay, so VLOOKUP, and then this is like what helps you figure it out. So if you know coding at all, these are called parameters. The search key, then the range, and then the index, and then asking if it is sorted. All right, so the search key, that's the name of the beam. Well, where do I have the name of the beam? I have it in this cell right here. So I'm going to click on the W12 by 35. Oops, it showed up, it went into the wrong place. click on the W12 by 35. So after all of this, the M12 should show up right there after the parenthesis. Okay? I'll do this again. I'm going to just hit escape. Equals V lookup, open parenthesis. Click on the W12 by 35. All right. Hit put in a comma. All right. Now it's going to look for the range. It's asking you, where do you want to look for this value? So I have to go to the wide flange beam table. Click here on wide flange beam table. And you want to check this entire page. The easiest way to do that is click in this box right here next to the left of A and above 1. It selects the entire page for you. Again, type in a comma. Index, well, that's the column I'm looking for. Remember, I'm looking up Z sub X. Well, that's my 19th column. So type in the number 19, hit comma again, and now it's asking, is this beam table sorted? And in actuality, it's not sorted. So click or type in the word false. And you see how false turns blue. Close your parenthesis and hit enter. And after all of that, the number 51.2 shows up. You can do two things to check if that's the right number. First off, this is the same beam we chose. And if you remember when we looked it up, yeah, Z sub X is 51.2. And also if you go to the beam table, go down to W12 by 35. W12 by 35. Oops. You know, it's going to help. What I should have done all along is freeze this, view, freeze, up to row 5. And now if I go down, I can still see that. W12 by 35, Z sub X is 51.2. Perfect. It looked it up for me the correct way. All right, go back to the interior beam table. So we're going to use this exact same formula. So I'm going to go up here to the formula bar, highlight it, Control C, go down here, double click into it, Control V. Double click into the next one, Control V. Double click into the next one, Control V. All right. I don't want it to look up Z sub X every time. I want to look up the depth, the web thickness, and the moment of inertia in the X direction. There's only one thing you need to change every time. It's the column number. Change number 19. So the depth, that is in column 3. So double click into here, highlight the number 19, change it to the number 3, enter. The web thickness, that is in column 4. Double click here, change the 19 to a 4. Enter. The moment of inertia in the X direction, in the X direction is column 13. So double click, change the 19 to a 13. Enter. And now, if I just verify all of this, because I already wrote all this stuff down, this is why I'm using it. Yep, D is 12.5. 12.5, 0.3, and 285. All correct values that I looked up before. All right. Now, it should be able to check for me. All right. Remember, I wanted my plastic modulus of the beam to be more than the plastic modulus I calculated I need. So the table should be able to look up, or sorry, the sheet should be able to tell me if I did the right thing. And there's a formula. It says equals, and it's an if statement. Equals if, open parentheses, a logical expression. Again, if you're in computer programming, this is like you're checking the value. Logical is like greater than or less than, or if true. So I'm going to say if the plastic modulus that I actually have this value is greater than or equal to this value, then I want my sheet to tell me good. In order for it to tell me good, I need to do open quotation, G-O-O-D, whoops, good, if it's three O's, close quotation mark. Otherwise, so that's value of true, and then otherwise, comma, if bad, tell me bad. Or tell me Sharv. I'm just joking, Sharv. And we're recording, so I shouldn't do that. All right, and then hit enter. And hey, I also got one extra thing already pre-programmed in here that I didn't tell you about. You can do conditional formatting. If you never use conditional formatting, you click on Format, Conditional Formatting. It's a way to color code your stuff. So I said, if the text is exactly, or you can do text or numbers or whatever. If I said the text is exactly good, change it to green. Otherwise, if the text is exactly bad, turn it to red, okay? So this is just a way, because I'm a visual person, if it doesn't have color, it's not gonna stand out to me. If there's any red in this sheet other than this beam thing here, then there's an issue, right? That says bad, so I should change it. I will later, but not right now. All right, now section K. I need to do this calculation, and again, it's another check. All right, so available shear stress. So I need my yield strength, that's my 50,000, so equals, click on the 50,000, enter. I need my depth of my beam. Hey, I just looked that value up there. Equals, click on the 12.5. I need my web thickness. That's my 0.3 I just looked up. Equals, click on the 0.3. V sub n, well, this tells me my calculation. 0.6 times f sub y times d times t, the web thickness. Equals, click on this. Oh, sorry. Oops. Before I click on anything, 0.6 times. Then click on the f sub y value, 50,000, times, click on the 12.5, and then times the 0.3. 112,500, 112,500. Again, if you look at your notes in section K, it matches. Applied shear load. That's this calculation here. Well, I've already calculated what my applied shear load is all the way up here. So click on equals and then click on the 24,000. 1.5 is just 1.5. Just type in that value 1.5. So the applied shear is equals 24,000 times your factor of safety of 1.5, 36,000. Again, we calculated that same value. Now again, let's have it check. Is the available shear strength more than the applied shear load? What you care about is V sub n more than V sub a. So again, it's another if statement. Equals if, open parentheses. Click on the 112,500, greater than or equal to 36,000. If that is true, tell me good. Otherwise, tell me bad. You just need quotations. If you're going to use text, you need quotations. It's, again, a common computer science thing. All right, hit enter. Oh, hey, look, even though I don't have enough plastic modulus, I've got enough shear strength. The beam needs to have everything be good. Plastic modulus, shear strength, and deflection. So if one thing is bad, the whole thing is bad. But hey, either way. All right, almost done. And hey, I think we'll finish this out today, actually. So the length, I need it in inches. Well, I'm glad I set that up back here. So hit equals, click on the 288 back here. Enter. The maximum allowable formula is L divided by 240. So equals 288 divided, so click on the 288 divided by 240, enter. All right, that's what I said again. I'm allowed to have 1.2 inches of deflection. Now I need to do this calculation. And again, I've already preset it up so that I'm trying to tell you, make sure it's the uniformly distributed load in inches. So equals, click on the WI over here, the 166.67. Enter. The length of the beam, again in inches. Click equals, click on the beam length in inches. E, Young's modulus for the steel. Click on equals, click on the 29 million. I, we looked that value up for the beam, the moment of inertia. Equals, click on I. All right, I'm gonna make this the center of my screen. I'm gonna zoom in a little bit so we can all see clearly. Whoops. This is just gonna be a slightly more complicated formula, not super complicated by any means. All right, so equals, open parenthesis, 5 times, click on W, times L raised to the 4th power. End parenthesis, divided by, so backslash, open parenthesis, 384 times, click on E, times, click on I. Enter. Not super complicated, just a lot of things to remember. And it's always good practice to use parentheses to isolate what's happening in your numerator compared to what's happening in your denominator. Hit enter. That's the same value we came up with by hand. And now for the first time we want it to be less than. Is the max expected? I should say, right here I could say expected. Is the max expected less than the maximum that is allowed? So equals if, open parenthesis, is the max expected, this value here, the 1.81, click on that, less than or equal to the 1.2, click on that value, if so, comma, good, otherwise, comma, bad. Hit enter. Uh-oh, bad. Zoom back out. So the whole point is now we have a sheet that can calculate any interior beam that we would ever need. Not only for this project, but hey, if you end up going into a civil engineering program in the future, the calculations don't really change. You could use this sheet again in the future. All you have to do now is verify that your dead load, your live load, your beam length, your beam width are correct, and also your steel properties. Make sure you're using 50 KSI steel and 29 million. Again, you have different strengths of steel depending on the project, different dead load, live loads, and beam dimensions. And then from there, it's just making sure you select the right beam, right? If I chose the W44 by 335, yeah, well, you better believe that's going to be a very big beam, very heavy beam. That is way over designed. That would be a terrible idea. Your client would be so mad at you for buying something so expensive. All right. So the whole point is you're trying to get this value and this value pretty close together. Okay. So if I try to find something that's almost exactly 57.72, as well as the smallest possible numbers here, this number and this number, that's where you're being an efficient engineer, an efficient designer. All right, so let's see. I'm looking for Z here. So that one's a little too small. 10 by 112, that's way too big still. Yeah, I guess the best thing to do would probably be, I could do a 61.5 if I do a 14 by 34. Yeah, probably that might be my best bet here to find one as close to 57.7 as I can. Yeah, so that's where I would go possibly is 14 by 38. Okay, so just scroll down till you find 14 by 38. Well, really, it's your call. 14 by 38, a little too much deflection. So even though it's strong enough, too much deflection. So not good. All right. And again, the calculations do this for you in a much better way. All right. So I should probably go back down here. Let's try the 12 by 45 and see if that's going to work for me. 12 by 45. That even got worse. So, but hey, this is where it's just, instead of you having to even redo the calculations, you're just guessing. And it's a lot easier to do that. And I think I can even type it in. 12 by 50. Oh, I'm still not getting there. 12 by 53. Oh, look at that, 1/100th of an inch off. That's where maybe as an engineer, you could just tell the whoever's checking your work, or like the whoever's reviewing your work, like the people who approve it, say like, listen, are you really going to get on me about 1/100th of an inch? But if we really want to be thorough, which in this class we're going to be thorough, we'll do 12 by 58. But again, in practice, that would probably be a good enough design. But there we go. Now we see all three green. Okay. That's it for setting up this beam table here, or this beam design here. You'll see that the other tables are almost ready for you. Not 100%. So we'll finish this whole sheet up and get ourselves 100% finished with this at the start of the next class. It should only take 10-15 minutes, and that should be it. If you have any questions, please let me know.